now that we have worked out how the code itself can be written and how it can be simulated, I am going to use one particular tool in order to demonstrate some aspects of synthesis, right. Now, in later assignments and in later especially in the lab, we will be making use of Xilinx tools, in particular the Vivado tool from Xilinx, in order to actually do synthesis. Now, Vivado is a it is industrial strength software, right, but it is also heavy software. It requires a very large amount of space for installation, and it is also comparatively slow. Instead of that, for the kind of examples that we are working with, I am going to be using an open source synthesis tool called Yosys, and this is something that, being open source, we could actually even go in there and figure out how it works, add extra optimizations to it if necessary. It actually forms an important part of an overall design process called open road, right. This is a open road and open lane are two different projects that were started somewhere among universities in the US in order to build up a completely open source based design flow. So, I will be using Yosys primarily to sort of demonstrate how synthesis can happen in the first place, and what we want to do with that is to sort of just look at what the output of synthesis looks like, right. Now, the way Yosys works is you need to read in your Verilog file, and then you need to give it a synthesis command, right. The synthesis command could be broken up into multiple stages. Either you can sort of go through and give it the individual stages, like do the basic processing, extract the finite state machines, do optimizations, do certain other kinds of optimizations and so on, or you could just go ahead and give it one command saying something like synth_Xilinx, which has a pre-built set of optimizations targeted towards Xilinx FPGAs, right. What I am going to do over here is to sort of run through and show you what what the process looks like, but then finally what we will be doing is there is a lot of output that it generates, most of which is not really relevant for us. So, I am trying to sort of look at which are the parts that are useful, that give us useful information that we can understand and build something out of over here, okay. So, the way that it works would be, so currently I am going to straight away show you the output that gets generated after I have run the Yosys synthesis on the two different codes that I showed you, right. One of them is, the first one I am going to look at is the parallel multiplier output, and we can open that file, and as you can see, there is a lot of information out here. It basically is fairly verbose. It gives you a lot of information about what it is doing, but it is also fairly structured, right. It first tells you that it is executing the front end, right, the Verilog front end, in order to read the file. It also tells you that it is generating some kind of RTL-IL representation. This is an intermediate language, right, which is defined for the purpose of using this Yosys tool, right. And essentially what it does is, you can already see that, for example, it says that it saw that stage sums was declared as a two-dimensional array which looks like a memory, but then it is replacing it with a list of registers, and the reason it is doing that is because of the way it gets used after that, right. You are not really using the individual memory elements separately in individual clock cycles, you are trying to use them all at once. So, it has to replace it with a list of registers. It sort of thinks this may not be what you wanted to do, because typically when we define two-dimensional arrays, it is for the purpose of creating memory blocks, hence the warning, right. All synthesis tools tend to generate a large number of warnings, and sometimes you will find that there are so many warnings that you just would prefer to ignore them. It is generally unsafe. You should make it a habit to pay attention to the warnings as far as possible, to at least make sure that you have an idea of why the warning exists and whether it is safe to ignore. It then says it's going to execute the synth_Xilinx pass, and there's a lot of information that then comes up out here, most of which we are just going to ignore. Most of which is actually talking about modules which clearly are not being used. For example, there's a 128-bit ROM element and some other DSP 48 blocks which are large multipliers, all of which clearly have nothing to do with what we are actually trying to synthesize. So clearly all that it's doing is generating this representation for all the internal blocks that it has, not just for what we are trying to run out here. Okay, but anyway, let's skip through all of this. As I said, it generates a very large amount of information, and what I actually need to do over here is skip all the way through almost to the end, right, which is where things start to get interesting. You can see that it's basically managing the design hierarchy over here. It first finds the top of the design hierarchy and finds that yes, it's parallel multiplier, which in turn contains adder tree and partial product generator, right. What are these things? It basically says 0 level means that these are the bottom level. Adder tree does not contain any other blocks internally, neither does partial product generator. But parallel multiplier contains these two as internal blocks, so it's at level 1. And it automatically selected parallel multiplier as the top module, right. We could also have specified the parallel multiplier as the top module, or we could have specified one of the others as the top module if we wanted it to focus on that instead. It picks up, in this case I have actually made a slight change over here. I changed the width to be 32, right, just to sort of demonstrate the difference between the parallel and sequential multipliers, right. It then goes through, yes, there is a lot of the processing pass does some kind of internal processing of the data, right. But once again, like I said, I'm going to skip through most of this, right. It's very verbose, it generates a lot of information. Interestingly, despite that, it is much faster than what actually happens in the Xilinx Vivado tools itself, right. Having said that, Vivado is meant for much larger and more complicated designs and does more optimizations, especially with regard to timing and so on, right. We finally get to the technology mapping, right, which is where we have now gone from the intermediate language, the RTL-IL, and we are starting to move towards the technology stack that we have, which is basically lookup tables, flip-flops, DSP blocks and blockrams, right. And essentially what it's saying is, it is going to map to what are called the technology primitives, which are essentially the blocks out of which an FPGA is made. So if we continue going down this, right, what we finally have is after quite a lot of scrolling through the different log files, we get the final statistics of what it has managed to do, right. And what we can see is for a 32 cross 32 multiplier resulting in a 64-bit output, it basically created a design that ends up taking something like 2800 wires, 10,800 wire bits. Well, this you need to sort of go in there and understand exactly what it means. But what is important over here is now these are the actual technology primitives, right. The LUT2 or LUT and the LUT2 is the 2-input lookup table. This is a 3-input lookup table, 4-input lookup table, up to a 6-input lookup table. These are the different lookup tables that constitute the internals of the FPGA. And as you can see over here, it actually ended up using something like 2406 input lookup tables, only 65 2-input lookup tables, but even a 2-input lookup table is actually implemented using a 6-input lookup table, right, because there are only 6-input lookup tables present in the FPGA. This is an estimated number of LCs or logic cells, which is sort of an abstract term that indicates a combination of logic cells, lookup tables and flip-flops and so on, right. But ultimately what it's managed to do is to take your entire design and convert it into a set of primitives or gates that correspond to what is actually present inside a Xilinx FPGA. One observation over here is that it talks about the different kinds of lookup tables, but nothing about flip-flops, which is as you might expect, right, given the fact that there was no clock and there was actually no notion of sequential element at all in our entire design. Even though we had for loops, as we saw, they just get unrolled out into combinational logic. So this is a completely combinational design, and the report that we see over here fits that expectation. So finally we end up with a design that has our the different parts of the design hierarchy. It basically tells us that this, for example, is the partial product generator, this is for the adder, right, and we finally have the overall system is combining everything together and giving us the parallel multiplier, which is estimated to take around 4000 logic cells, right. Now is that a large number? Well, we don't know, right. Maybe it makes sense because the 32 cross 32 multiplier is roughly 32 into 32 or 1000 different partial product elements and gates or at some level, plus the multiplexers and various other things that are required for it. Maybe this number of logic cells actually makes sense, right. We will have to sort of compare it against other known designs in order to see whether this is the best that can be done. Now that is as far as the design is concerned, right, and as I told you, the important thing that is required is to sort of understand what are the different kinds of cells and how many of those are roughly being created for us, right. One other thing which is useful to understand is this pass number 4 over here in this case, right, which basically says it's STA or static timing analysis. Now the first thing is it basically complains about a few things having no timing arcs, right, basically saying that okay, it does not have any information about the timing for these, but more importantly it also says that critical path essentially does not seem to have any registers associated with it, right. So it is not able to find any kind of registers through this design. It has still done some kind of an analysis and found that the latest arrival time, right, is 3315. The units in this case are basically picoseconds, right. So it is around a 3.3 nanosecond delay through this multiplier that we are talking about. How did it come up with that? Because it has some information about the delays through individual lookup tables in Xilinx FPGAs and some estimate of what kind of routing delays would come into play. And based on that it comes up with this number saying it is going to probably take 3300 picoseconds or around 3.3 nanoseconds in order to perform one multiplication. This is the minimum, the guaranteed delay that we have through the entire system, or rather the maximum guaranteed delay, right. So as long as your clock period, if you take this multiplier and try to put it in a larger design where its inputs are coming from a register and the output of the multiplier is going into a register, you should ensure that the clock period is at least this many picoseconds, 3315 picoseconds, plus the setup time of the flip-flop, the TCQ of the previous flip-flop and so on, right. But the one thing is, of course, it's sort of complaining, saying that it has to give you this, it is able to give you a critical path length, but it's not convinced that this is the correct answer because it did not see any TCQ and T setup corresponding to registers over here. Still, we know that this is a combinational circuit, so at least this gives us an estimate of what the delay is. Alright, so now that we have all of this, let us also look at a similar output corresponding to the sequential multiplier, right. And what we have over here is everything looks pretty much the same. It basically parses the multiplier input, executes the synthesis pass. A lot of the information remains essentially identical, right, because it is doing a very similar kind of process over here as well, right. And what then comes up is there are a couple of things that you can notice over here, right. The interesting thing is that it suddenly seems to have found out about a finite state machine, right. And in fact, there is a lot of information out here. It basically says FSM detect, it was able to find a finite state machine. It extracted the finite state machine, it found all of these states and as well as the transitions. And after it has done that, it basically identified all the different transitions that were over there, right. So from state 0 there is another transition to state 0 based on all of these as the different inputs that are there to the FSM, right. What were the inputs? It was all the things like the start signal and various other kinds of things that we had, right. Now as you can see over here, it has states 0, well it has 1, it has 2, 3, 4, 5 and up to 6, right, which makes sense. We basically had that many different states over there, and the enumeration that we had basically did that directly. But now is when things get interesting. It decides that it doesn't like this state encoding and it's going to do a recode, right. And as I mentioned before, in FPGAs flip-flops are plentiful, so rather than trying to optimize anything, it basically decides to go for a one-hot encoding, right, and says okay, let's take state 0 and convert it into this encoding which has a 1 in this particular bit and everything else is, well, blank, but basically, and I don't care what the values of the others are, but they should be zeros, right. And by doing that, we are able to essentially find out that there are 7 state bits that I need because I have explicitly taken the 7 states and encoded them separately. There are 4 inputs, 7 outputs corresponding to the state machine, and it then does some kind of optimizations and finally comes up with the optimized transition table. All of this is automatic, and this is partly the reason why I said it is not really worth trying to do an optimum assignment of FSM states or encodings while you are writing your code, because the compiler will detect the FSM for you and do a re-encoding anyway unless you force it not to, right. There are ways of sort of overriding it and telling it not to make any of those changes, but that's generally not helpful in most cases, right. It's better to let the compiler do this because those are tasks that can be automated quite well. Alright, so once we have done that, we then get back to the regular process of optimization of the rest of the design, and we finally come to the synthesis results just like we had for the case of the parallel multiplier, right. Yeah. So the statistics over here are, once again you have something about wires and so on. What is interesting over here is in this type of cells that we have, right. You can see that the buff-G, carry-4 all remain the same. FD was something that did not exist in the other design, and FD basically refers to a D-type flip-flop with a clock enabled, right. So these F and FDPE is also a D-type flip-flop with some other kind of enable. I don't recall exactly what it is at the moment, but both of these are different kinds of flip-flops. So you can see that there are a bunch of different flip-flops used over here. In fact, there are 114 of them. If you go through, then you should be able to actually identify exactly where these flip-flops are being used. For example, 64 of them are definitely being used for the product register, another 32 for the multiplicand register, another 7 of them at least for the state, and there are a few others that are also being used probably for the individual output signals, and you will need to check and verify whether they add up to this number that we actually have over here, or whether there is something that we have missed. It's usually good practice to do that, just to be sure that you are able to justify why a certain design took a certain number of resources. You can see that this is also a 32 cross 32 multiplier, but it only took up 113 logic cells as opposed to the 4000 odd that were taken up by the parallel multiplier. The reason being, we are basically reusing resources very dramatically, right? And the number of cells or the area basically grows quadratically in the case of the parallel multiplier, but in the case of the sequential multiplier, it just grows proportional to the number of bits that you have. Now, if we go through and then look at the timing analysis, right, in this case it doesn't quite have that complaint about no critical path found, but there are a couple of interesting things that you can observe. One is, for example, the fact that the latest arrival time, which basically is sort of the most critical path that it has been able to identify, is 1.6 nanoseconds as opposed to the 3.3 nanoseconds in the previous case, right. This does not have a complicated adder tree. So that basically reduces the delay quite a lot and brings it down to around 1.6 nanoseconds or so, right. Now this is not entirely accurate for the simple reason that Yosys does not have a very good, does not have a complete database of the individual routing delays through the different wires and so on, right? That can be modeled only after we have some more information about how it's actually going to get placed on the FPGA, but this is a fairly good first level estimate. So what we can see is it is going to be faster in terms of the maximum clock that can be run, but we know that it's going to take far more clock cycles, not just one clock cycle, in order to get a result. So at the end of the day, the parallel multiplier is still faster in terms of getting your final result, but the individual clock period that you can use on it is significantly slower than what can be done with this sequential multiplier. Hardware resources wise, this is massively better than the parallel multiplier. But if you were only doing an 8 cross 8 multiplication, the story would have been quite different, right? The parallel multiplier would have also been reasonably small and the discrepancy would not have been so dramatic between the two. Right? So anyway, this is to illustrate how you can sort of interpret the data coming out of a synthesis report and out of the timing analysis report, and we will be doing more examples of these as we move forward, and also using different tools like Xilinx Vivado, for example, in order to do that.